we have a couple more vocabulary words to talk about in the simple machines unit. And then the fun stuff of actually playing with the simple machines will start. But first, one of our vocabulary words is energy. Now remember, in physics, we use some words sometimes like acceleration, and they mean one thing in physics, but then we use them another way in our everyday lives as lay people, as regular people who are not scientists. So keep your mind open when we're talking about these, and don't assume that energy just means having some energy. Although you can see the relationship here. Energy is the ability to do work. That's the definition of energy in physics. And you can see if you have some energy, yeah, you could get up and do some work. So in that case, there is a connection there. But in this case, work is not just like something that has to be done, or getting up and going to the office or the job site or whatever it might be. But work, as a physics definition, work is energy transferred by force. So think about this as a hammer doing work. A hammer has energy that is being transferred by force into the nail head to drive the nail down into the screw. So work is, as a mathematical equation, work is force times distance. And you can remember that the way we did the ramp here. So the amount of force being applied to this rock over how much of a distance. So if I were to lift this rock, if I were a little tiny person like these Playmobil people, if I were to lift this up onto this platform, that would require a tremendous amount of force to do so, but the distance is not terribly great. Or I could use the ramp and apply a lot less force over a greater distance to achieve the same thing. These two definitions are somewhat circular in nature, which means that they're kind of involved in each other's definition. Work has energy in it as the definition, and energy has work in it as the definition. That's not a bad thing that they're circular. It makes it a little bit harder to understand sometimes because the words are, you're using the same words over and over again, but they are that related to each other. So it's not a bad thing that it is a circular definition. Right. When we talk about simple machines, we often talk about mechanical advantage. And what that means is how effective a machine is in doing work. And this could be for compound machines or simple machines, a mechanical advantage. But for the purposes of our class, we're talking about just simple machines. So mechanical advantage. If we grabbed a lever, how effective is that lever in doing work? So here's what mechanical advantage is. The mathematical formula is resistance divided by effort. So mechanical advantage is resistance divided by effort. Resistance is that which needs to be overcome. In this case, it could be the weight of that rock that needs to be lifted onto the platform. Or sometimes you'll see resistance in electricity. For example, have you ever made toast? What makes those little wires inside the toaster get so hot? Well, you might say, well, duh, it's electricity. But what is happening there is that the electricity is flowing into a special type of wire that's usually made of like a nickel-cadmium combination. It's an alloy, a blend of metals. And it does not conduct electricity very well. We say there's a lot of resistance. It is resisting the flow of electricity through that wire. And so the wire gets really, really, really hot. And then the wire glows, and that gives off heat so we can make our toast. So resistance is that which needs to be overcome. In electricity, it can be almost like the wire not wanting the electrons to flow through it. Or in this case, it is a weight that needs to be moved or something of that nature. So back to our mechanical advantage now. So in this drawing, we have our resistance is the weight that needs to be moved. There's a box that weighs 210 pounds, and there's a scrawny guy trying to move it, and he is applying a force of 30 pounds. Remember that mechanical advantage is resistance divided by effort. So if we turn this into a math equation here, we would say mechanical advantage, it's here, mechanical advantage is the resistance, 210 pounds of weight, divided by effort, which is the 30 pounds, and then just a simple division, we come up with the mechanical advantage of 7. So the 7 probably doesn't mean anything to you, but what that does for us is it gives us ratings of mechanical advantage that we can then use. So a certain ramp might be a rating of 3, another ramp might be a 2. And then you know that the 3 has more mechanical advantage and would better serve you in your trying to move a weight or like a rock up a ramp. All right, 2 other vocabulary words that we need to cover. The first one is kinetic energy. Kinetic energy is in motion. Anytime you see the word kinetic or something like it, like kinesthetics, that has to do with motion. So kinetic energy is energy in motion. When a hammer is moving through the air, it has a lot of energy to it that it can then apply to driving a nail head. The opposite of that is potential energy, and you can see the person camping out next to it. Potential energy is stored energy. It's camped out. It's not going anywhere at all. And there's 2 types of stored energy. There's actually a lot more than that, but we're going to talk about 2 of them. One is gravitational and one is elastic. All right, let's talk about potential energy a little bit. Potential energy, remember, is stored energy. And this is an example of gravitational energy. So if we had a box that weighed 100 pounds and it was in the air 10 feet over our heads, here's our floor here. Perhaps it's attached to a pulley or something running up and coming down to a line somewhere else. So however it's up there, it's just hovering in the air at 100 pounds. So the potential energy is that this is gravitational stored energy. It is, while it is sitting up there, it does not have any kinetic energy. It's not in motion, but it has the potential to have a lot of kinetic energy if it were moving. So this is stored energy. It's called potential energy because it has the potential to do a lot of work, but it's not doing any work right now. Picture yourself, since we live in water communities all around here, maybe you've seen a dock being built and workmen driving the pilings of the dock. See, this is a perfect scenario of that. Let me grab a marker here and see if I can film and draw this at the same time. So there is a device that is attached to a crane over here. And here's our big crane. And that's sitting on a boat. And the crane can lift this 100 pounds up and drop it over and over and over again into this piling, and it's going to pound it over and over and over again like a hammer, and it's going to drive this piling down into the seabed so that you can then build a dock with it. So while it is sitting up here in the air, it has potential energy. It's not doing any work. But then when we release that potential energy, let the 100 pounds fall, now it has kinetic energy, which can do a great deal of work. When we talk about potential energy, let's drop down here and do some math here for a second. When we talk about potential energy, there is a mathematical equation. I don't need you to be able to do this on a test, but I do want you just to have some understanding of what we're talking about. So when physicists do this, potential energy is the mass. Remember, that's kind of like how dense something is. In this case, we can say it's how much something weighs, times gravitational acceleration. That's a physics constant that it's just always the way it is on Earth. It would change if we were on the moon or on Mars or out in space. And then times height, how high the object is suspended above the ground. So if we start plugging in our numbers from our situation here, we put in 100 pounds times our gravitational acceleration constant. That's 9.8 meters per second, and that's not something you can figure out. That just is what it is. That just comes from physics. And then times 10, which is our height. So I'm using the same equation up here, just plugging numbers in now instead of words. And then we'll do the math. I'm going to do this side first to make it easy on myself. I'm going to move the decimal since I'm multiplying times 10. I've got 98 meters per second times 100. 100 times 98 is 9,800. And then the measurement that we use in doing this can either be called Newton meters, where we would write an NM, or it can be joules. Either one is right. So I just want you to see that, just to have some understanding of potential energy, that we are taking the mass times the gravitational acceleration, which is the 9.8 meters per second constant, times the height. And that's what tells us how much energy something has potentially to do work. All right, we're back again looking at our 100 pounds of potential energy up in the air. It's 10 feet off the ground. So what if now we took it and we dropped it down to the ground? If it was the machine doing the work, if it was a person holding a pulley, whatever the case might have been, if we let go and let this 100 pounds drop to the ground, it's now gone and it's sitting down here. So kinetic energy happened in this space here. Work was done as this fell. And now down here at the bottom, we can say that the potential energy equals 0. Because there is no potential energy now. There is no potential for work to be done when a 100-pound object or when a feather is sitting on the floor. It can't go anywhere and do any work because all the gravitational acceleration potential has already been used. All the mass is at rest and no longer has any potential. Can you see the difference here? Potential on the left side, 100 pounds hovering in the air. It can fall into a tremendous amount of work. Once it has already fallen, until we lift it back up again, it can't do any work, and so there is no potential energy whatsoever. All right, we talked about potential energy. We've talked about gravitational potential energy. The one we didn't talk about is elastic potential energy. And then there's also other stuff like chemical potential energy and those kind of things, but we're not going to get into that in 7th grade. That'll come later in your high school and college years. But elastic potential energy is the idea of a spring or an elastic material like a rubber band. So again, when I stretch it, it's loaded up with a lot of potential energy. It has the potential to do a lot of work, but it's not doing any work at all. And then if I let it go, like if I was going to shoot it like a classroom naughty boy, then it's kinetic energy. I've released the energy and off it goes. Or likewise, if I bring it back to smack you with it, then it's going to do some work and it's going to hurt.